So can we start or we can wait for another 1 or 2 minutes?
No worries. I'll just try to see if I can set up
Okay.
my.
So it's 7:37. So we will start at 7:40.
Oh, 7:40, like in half an hour.
No. 7:37. Only 2 minutes.
Okay,
You can.
sure.
It's
Yes, yes.
7.
Okay, sorry.
It's
It's because it's
7:37
7 a.m.
IST.
in Vancouver. Yeah, that makes sense.
Yeah.
But can you
So
see
we'll
this
just
is
wait.
sure? But is this correct? Like that's the you see the page at the moment?
Yeah, yeah. The
Okay,
poster is visible.
okay, perfect. So that's the title. I'll leave it on this.
Okay. Now we can start.
Okay, thank you so much.
Okay. Good evening, all. Myself Chiranjeev Sarkar, Vice Chair, TAIym. So, on behalf of TAIym committee, uh, we are welcoming you in our next webinar, WBR 26. So today's topic is TBM partial excavation design and rural challenges by Mr. Keivan Rafie. Mr. Keivan Rafie is the Deputy Regional Director for Hatch Tunnel practice in Vancouver, and he has more than 20 years of experience in tunneling, mining, and ground improvement projects. He has been involved in projects in Canada, UK, Middle East, Australia, and United States, using tunnel methods such as drill blast, ACM, TBM, and a range of tenseless methods. So now we welcome Mr. Keivan Rafie for his today's presentation. Mr.
Thank you
Rafie,
so
over
much.
to you.
Thank you so much for your introduction. As you said, my name is Keivan Rafie from Vancouver Hatch office. My background has always been tunnels from my first job in 2001, and since then I've been moving around the world to gain more experience both on the design and construction aspects of tunneling. My presentation today is about the number of interesting challenges we faced in Brisbane, Australia for the Airport Link Highway Tunnel project. I got involved at the design phase of this project, around 2007 and continued my involvement into the construction phase until 2011 before I moved to Canada to work on Spadina subway in Toronto. Do you hear me well? Everything's okay? Video, the slides and the audio?
Yeah, the
Yeah,
video
it's
is,
audible.
the screen is fine, but your can you just adjust your mic a bit?
Yeah, sure. I can take my headset at let me work.
Yeah, that will be great.
Sure, just a second. My apologies, I didn't seem to find my headset right now. So I'll just try to speak louder if that's okay.
Yeah, it's fine. It's fine. Thank you.
Okay.
Thank you for the cooperation.
Thank you. All right, so let's start. Sorry for the delay. So for those of you who haven't been there, here's the more or less accurate map of Australia. Brisbane location is shown with the arrow. So Brisbane is only 40 minutes to Gold Coast, which is the tourist hub with lots of beaches and nightlife. So you'll have a great time there. Here is a nicer view of Brisbane downtown at nighttime. The south end of the project starts just behind these buildings. So in 2008, the government announced that the JV composed of the Macquarie Group, Tees and John Holland, been selected for the Brisbane Airport link. The project involved total of 15 kilometers of tunneling, including main road that includes 6 kilometers of twin tunnels, busway tunnels, and connecting on and off ramps, as well as 25 bridges, resulting in over 7 kilometers of new road. Now, to focus on the title of this presentation, let's focus on the area that partial excavation was performed. Here's the general map of the project. Bowen Hills in the south is the area just north of the downtown, and Toombul in the northeast is where the airport is located. Around end of 2008, tunneling first commenced on the project with drill and blast excavation at Bowen Hills, and also with road headers in Kedron for entry and exit ramps. TBMs were launched at Toombul to mine in southeast direction, and passing the North Caverns in Kedron area, and to finish when breaking through the South Kedron Caverns for the second time in their journey. So here's a 3D model of North Caverns. As discussed, along the alignment, both TBMs were required to pass through North Cavern at Kedron area that had been excavated through sequential excavation method by road headers or drill and blast method for the base of them, which is shown by yellow arrow here. As you can see, these large caverns were designed to connect the entry and exit ramps about halfway along the tunnel. Here's the photo showing the average size of the cavern excavated using STM method. We can see waterproofing arrangement and some sophisticated concrete forms that needed to adapt to different profiles as they've been pouring concrete along the tunnel. Here is a view of a two-lane ramp joining a two-lane main line tunnel in Keivan area. So that's where the people who want to go to the airport go straight, and if you want to take off, go to the off ramp. So ground conditions for the TBM drives consisted of a fairly complex geological settings. It comprised of alluvium, sedimentary materials, carbonaceous siltstones, and conglomerates underlain by a tuff that was called Brisbane tuff. The groundwater along the alignment comprised of two main aquifers and stood around 35 meters above tunnel invert on average. Each TBM was designed for 2.4 kilometer of tunnel excavation with a minimum curve radius of 750 meter and a working pressure of 4.5 bar. The cutter heads had a bore diameter of 12.5 meter approximately, and each weighed about 200 tons. The cutter head tools consisted of disc cutters for hard rock portion of the drive and the scraper and buckets to deal with the soft ground. The TBMs had 38 main truss cylinders, 19 rams in total with 2.8 meter of stroke and 90 meganewton of thrust force. So following the arrival of the project's first TBM from Germany, Herrenknecht, machine assembly soon got underway. By March 2010, both the cut and cover structures and the TBM launch box at the north end of the project had been completed. So the two TBMs began their approximately 2.5 kilometer long drive, going southwest from Tomball towards the Keivan cavern. So what you see in the picture is the TBM just launched. So it's about like 200 meters of it is gone in, and just you see the last gantry, which is still very close to the portal. So here's again the 3D figure we had before, now showing where the TBMs had to break through the already excavated with the caverns with the STM method, shown with yellow, and then where they needed to relaunch for the second round of full face excavation, which is shown by green. So after 12 months, Rafie, one of the TBMs, reached her target in July 2011, while Sandy achieved the same target 2 days later. In order for the TBMs to pass through the Keivan caverns and prepare for second launch at the opposite end, a few options were considered. So the first option was to just slide the TBM through the caverns on the cradle and rails. Another option was to disassemble the whole TBM, move the parts, and again put the pieces together. And the third option involved partial excavation, which is the topic of this presentation, in which the TBMs would excavate the invert of the cavern, so they can use their own rams to push off the precast segments, which is just on the invert, just at the bottom, around 6 o'clock. And so after weeks of planning, risk, and cost assessment and comparison between the options, we chose the partial excavation as the best option. One of the major benefits and reasons of selecting this method was that we could lay down the road decks, which were supposed to be constructed anyway, which will be used later on as the utility tunnel for all the utilities and systems to go underneath, and also a drainage path. So because we had to lay down those rakes anyway and extend the utility tunnel, there was no interruption or no difference to if with the normal excavation. So it worked for us both ways. Here's a quick glance on how it looks like in that cavern, where you see that the TBM has already excavated the invert for some meters. You see the top of the cavern is above the TBM. So this is the cavern that's been constructed before manually by STM and excavation and supported with rock bolts and shotcrete. And then this is the TBM that's coming through that cavern. Or as we called that, we said we made the TBM crawl, so to speak. And then, of course, you see the guy there standing and not working and hiding from the manager is me. All right. So to push and steer the TBMs, we had to install precast segments at the bottom of the curved excavated profile, as I said. So we had to design a sequence of half rings. So as you know, the rings are usually universal, and then they go left and right. If you want a straight, you put left, right, left, right. So we had to do the same things for these half rings to design it like the ones that go left and right. And then because the cavern itself had some curvature too, so we had to navigate that. And this arrangement basically neutralized the taper and and also let us go through the curves. So then TBM could advance using the selected lower propulsion cylinders. We had to make some adjustments to the TBM, and then so we could steer the TBM through the cavern. As you know, normal TBM operation involves working with the TBM rams in groups. So we had to work with Terrain Connect electricians to modify the TBM software to say which rams exactly we want to push and then group them separately to the left or right so we can navigate. The other main challenge was the part with the partial excavation was the chance that it could potentially the TBM could potentially sink into the ground. This was experienced on some of the previous projects that they tried that. So you see the calculation showed that the TBM needed the support or minimum invert thickness to stop the forces on its center of gravity from causing the TBM to tend to move downwards. Additionally, a mock extraction strategy in front of the TBM required the one-way rotation of the cutter head because I'll show you the next photo and you saw in the previous one. One side of the TBM has some room, and because the TBM cannot excavate itself, the material other than the what's in the bottom of the screw, a lot of soil and muck, they just get dispersed around the TBM. So for these two reasons, we had to make some interesting modifications to the TBM. So the first element was using the concrete curb, we called it, and poured on both sides of the TBM along the cavern to resist the forces causing TBM to sink into the ground. So you'll see here we made some and the second element was the set of special anti-roll sink brackets that welded to the TBM shield, and they could slide along the curb, preventing the TBM from sinking into the ground, or also rolling while the invert was being excavated. Because as I mentioned, the TBM could only roll one way, so all that scattered muck can be on the side that another excavator can come and load the trucks with. So another concern or complication with this arrangement was for the TBM movement through the cavern was supporting the or flying backup gantries, because as you see, the gantries they would have to sit on the segments with some brackets. So the middle part of the TBM could just move along these rails. So these gantries by default move on the wheels, and these rails installed so they can be pushed forward. With the partial excavation, the half rings were designed to be extended a little bit above invert to at least for every second of them there is a place that we can put those brackets so the rails can be installed and the TBM can move. So that was another design challenge. And then after the TBM move, the half segments were need to cut to match the profile of the rest of the cavern. So we have the full invert of the tunnel for the cars in the future to pass on. So saw cutting of the segment was performed by mounting the horizontal rail on the previous and following segment, and then using a circular saw to cut the segments with high precision. My apologies, Vancouver these days very hot, but also they never had this temperature, so there is no air condition in 90% of the houses and apartments. So it hit us hard. All right, so the next slide, extracting the material in front of the TBM, also revealed some challenges that I mentioned. The most important, these were involved collecting the muck from the left and right side of the TBM. So on the side closer to the cavern wall, the excavators had difficulty reaching the materials that stuck between the cavern and the TBM. And on the opposite side, the excavated material was dispersed widely, and the excavator operator really had difficulty efficiently filling the buckets. So so those were other challenges that we faced. So we had to, for that challenge, we had to propose two ideas to efficiently progress the operation. The first idea was rotating the cutter head only to the side that to the easier side for excavator to take out the muck. And then also we modification was something we call them hungry boards on both sides of the TBM, which basically pile the muck for the excavator operator to help him load the trucks easier. So the other interesting element was transferring the material muck from the in the chamber from the TBM through the belt conveyor, because the cavern invert was preparation and certain other operation on the connecting ramps needed to be performed as soon as the TBM gantry had passed the area. But the conveyor belt, which extended behind the TBM, was restricting the access for all the rest of the work. So we had to elevate the conveyor, which we called at the time the flying conveyor. Okay, so and of course, not everything went smoothly. Just as we were ready to celebrate the end of partial excavation for the first TBM, with less than few meters of the southbound cavern left to be excavated, the southbound TBM or Sandy became entrapped in the smaller pre-excavated relaunch profile. So you see the figure here. This is a pre-excavated profile that was originally mined by Roadheader in advance to accommodate the design for the relaunch of the frame and other elements. So TBM can start full phase. The relaunch procedure, in brief, consisted of disassembling anti-rolls and cutting off the hungry boards, welding new hard-facing blocks and new tailskin brushes, installing the truss ring for relaunch, building full rings until the cutter head contacted the face, the new face, the relaunch, and then resume excavation for a final drive. So the chain of events that led to the TBM jam occurred around ring 719. The TBM entered the smaller sub-tunnel profile and was close to its final position for relaunch. The survey revealed that the TBM was slightly higher than the designed tunnel alignment, and the TBM operator was asked to center the TBM before the cutter head stopped for relaunch preparation, so we could start exactly where we needed. Within the few rings of final position, the TBM operator used a sharp overcut to return the TBM to the center. At that stage, the top section of the TBM shield had a small clearance with the roof of the stop tunnel. And at the same time, the TBM still had no back support other than those invert ramps. So you could only exert 10%, 15% of the capacity. That caused that was the reason for jam. So the friction after the top of the TBM hit the roof of the cavern, the friction which stopped the TBM, usually in typical projects, if you have a full face and you have all your ramps, that would have not been a large enough friction to stop the TBM. But in this case, because we only had the bottom ramps, and the more we pushed, actually the TBM tend to go up and actually get more stuck in that area. So just looking at this photo, I remember trying not to look 12 meters down in the dark while standing between the TBM bulkhead and the cutter head. So we tried, using the available rams in the bottom section of the TBM to release the TBM. The operators also tried applying maximum force to the left side and right side of those invert rams, just to jiggle a little bit, see if we can free the TBM. We also tried to release the TBM by pumping bentonite and jackhammer it, but when it was clear that none of those would work, then we had to think about something more serious or some other design solution. So we come to the conclusion that we have to be able to use the other rams of the TBM, both so we can get it aligned going down and also to push itself free from from where it got stuck. So after all that, we came up with this block. This block of concrete was attached to the roof of the cavern with 12 steel bolts that were inserted deep into the rock at an angle, such that when the TBM applies force to the truss block, the block will react in tension and transfer the loads into the ground. So the truss block was reinforced with rebar and poured with concrete after installation of the bolts. Later, when the concrete reached the required strength, all the bolts were pre-tensioned and tested for a minimum of 5 minutes for 100 kilonewton to verify installation quality and the anchorage in rock. So next, extension struts were installed to fill the space between the truss block and the truss cylinder pads. In this manner, the forces were shifted to the truss block and then to the rock through those tension through the tension in those bolts. So once the installation was complete, cutter head was retracted by approximately 100 mil, and then the overcut was set to 0 just to make the best conditions for the release. The solenoids on the top rams were also reinstated, so we could have those rams at the top. And then when we applied all that, we were successful to break the TBM free. So now I have 2 time-lapse videos. The first one shows the partial excavation in that cavern, about 36 seconds. And then the second video is actually something we didn't get a chance to talk about in this presentation, which needs its own presentation, but just to because it's an interesting video, that how we at the end of the project we buried the TBM, of course taking all the important elements out, but the shield of the TBM, because it was cost less for us to just to bury it in than just take it all the way out and torch it out. So with that, I hope you also get the sound, but it's just the music, so it's a time lapse. Hope that's interesting too. So you see here, the TBM just came to the cavern. There are, changing cutters and maintenance. You see the excavator that just taking muck in front of it, and then this scene that you see the TBM goes into the tunnel. You never get to see that scene because it's very rare that the TBM is in another cavern that you can have that view, and you see the half segments that are installed now, and then they get cut to get even with the rest of the floor, and then at the end you just saw the chains for that flying gantry. The next one, yeah, it's a burial of the TBM. And that's it. Thank you so much for your time, and happy to answer any questions you might have.
Hello.
Hello.
Yes, Mr.
So
Keivan.
that was the end of presentation. Hope you all enjoyed, and yeah, please let me know if you have any questions or anything to discuss or anything you want to ask from the videos. I can provide some more commentary.
Mr. Kevin, I have a doubt. I just have one single informative question. Like, what was the diameter and the thickness of diameter of the TBM
The
and the
diameter of the TBM was about 12.5 meters, so almost yeah, like a four-story building.
yeah, 3 story, almost like a 3 story.
I think so. You see there.
And what was the thickness, proposed thickness of the invert segments?
The segments were 400 millimeter thick, and yeah, you can imagine they were very. I think there were 7 or 8 pieces, and you can imagine the segments were really, really large. So had very specialized vacuums were needed for the rebuild. Get very heavy, and then the segments were mostly done by fiber reinforced. Fiber reinforced, but just the segments around the cross passages, because they need to take more load. We had like a full rebar in them.
Okay. Okay, thank you, Mr. Kevin. Um, any of the participants, do they have any doubts? Hello?
No, sir. No, sir. Thank you.
Okay, thank you so much. I'm happy to just.
Rohit, can I ask one question?
Sure, go ahead.
Kevin, can I ask that what kind of material is you encountered during the excavation? It's a kind of soft or mixed one?
We had. Let me go to that geotechnical. Where was it? Oh, there we go. So from what you can see, we almost faced everything. So when we started, we were actually in soil. And as we were going down, we were in the topsoil and some sandy material, some granular. And then halfway through, we hit this conglomerate and tuff area, which was hard rock, and up to, I think, between 100 to 160 MPa rock. So when we were in the soil, our face tools were more of the scrapers and the soft soil tools. And before we get to the rock, we changed the face of the TBM to have more disc cutters, which more suits for the rock excavation.
So basically, we are changing the cutter as per the strata encountered, correct?
Exactly, yeah. But we knew exactly where we would, because there were a good geotechnical investigation program. We almost had boreholes every 50 meters. So it wasn't like we just faced it. We knew exactly what we would have before we even start.
So we are already ready for that kind of geology for our triviums.
Exactly, yes.
Okay, thank you.
Okay.
Does anyone else has any doubts?
So Arushi, I can also later on, if you remind me early next week, I can send the slides, the PDFs to you. So
Yeah,
happy
sure,
to share
sure,
it
sure.
with everyone. And still, you
Yeah,
have
yeah,
my
yeah.
email. Any questions, anything you had, let me know.
Yeah, we'll email you the questions once we have it, and we'll be also sharing this webinar's recording on YouTube, and we'll share the link with you as well.
Thank you so much.
It was a pleasure having you, Mr. Kevin, on our platform, and thank you.
No worries. Thanks so much. Take care.
Thank you. Take care.